This section is about forces acting on flying objects: weight, lift, drag, and if you've got an engine, thrust. So you're flying in a glider. Why don't you plummet to the ground? We've already seen that things accelerating under gravity eventually reach terminal velocity when the drag matches their weight. This time we've got a different force slowing our descent to the ground. It's called lift. Drag and lift are both caused by the fact that you are falling through something, the atmosphere, air. Drag, lift and weight are all vector quantities. Weight acts towards the centre of the Earth, drag opposes the direction of travel, and lift is at right angles to the direction of travel. In a glider, we want drag to be as small as possible and lift to be as big as possible to ensure a long, gentle glide to the ground with no plummeting. Drag and lift are complicated forces and lots of things affect them. Properties of the glider, such as the shape of its wings, properties of the air, such as its density, and properties of the motion, such as the angle of attack. One way to understand lift is by considering the Bernoulli effect. Bernoulli's principle is a statement of conservation of energy and states that the pressure plus half the density times the velocity squared is constant. In other words, if velocity goes up, the pressure goes down. The shape of a glider wing is such that it causes air to flow faster over the top of the wing than the bottom of the wing, and we can see this as streamlines being closer together on top. If the air velocity is bigger on the top of the wing, Bernoulli's equation implies that the pressure is lower on the top of the wing than the bottom of the wing. This difference in pressure causes the lift force. We can see examples of the Bernoulli effect as a somewhat counterintuitive result when there is a high-speed airflow. It's the reason why you'll feel a jolt when you're on a high-speed train and another high-speed train passes you going in the opposite direction. The fast-moving air between the two trains has lower pressure and therefore there is a force pushing the trains together. It's also the reason why you can stably suspend a ball in an airstream. Low-speed air on the outside of the airstream has a higher pressure which provides a restorative force to push a displaced ball back into the flow. It's the reason why when you blow over the top of a tissue, it goes up instead of down. Finally, we've said that the shape of the wing is important to make the flow faster over the top of the wing than the bottom of the wing to generate lift. If we turn the wing, also known as an aerofoil, upside down, we can generate a downwards lift force. This downwards lift force provides important traction for cornering in race cars. In fact, the downwards force generated in racing cars is so big at high speeds that, in theory, you should be able to drive a Formula 1 car upside down on the roof of a tunnel. Things get sucked into high-speed flows because the pressure there is lower.